Hi there, welcome to this video. This is the next in the series helping you to prepare for Maths A Level this summer. And in this video, I'm going to have a look at a typical modelling question, and these can involve and apply to lots of different areas on the course and are coming up more and more in past papers. I hope the content of this video is useful and your revision is going well. A click to like the video at some point while you're watching is greatly appreciated. So what to do when you come to the modelling questions? Don't panic because they often look much worse than they are, and often parts A and B can lead you nicely into what you actually are trying to do in the harder part of the question towards the end. So let's have a look at some questions and let's get started. In this first modelling question, we've got this graph which shows the trajectory of a rugby ball. The ball is being kicked from the origin and lands 40 metres along, and it has a maximum height of 12. In part A, we're being asked to find the quadratic equation. Now we can see we've got a negative quadratic, but if we just have a look at a positive quadratic that might go through 0 and 40, so we could write h is equal to x into x minus 40, and where that equals 0, we could see that x would be 0 or x is equal to 40. That is the roots of our quadratic. But we have got the negative quadratic going through 0 and 40. So what we can do is say h is equal to x into, and then just swap them round. And then that again will give us the roots x equals 0 and x equals 40. But when we multiply this out, it's going to give us our minus x squared. Now it's going through at 12 high, and we don't know when we multiply that out that the coefficient in front of x squared is going to be 1. So if we put an a here and then use the information from the question to try and find a. Now when you've got a quadratic and it has its roots and we've got them at the origin and 40, halfway between them is going to be the line of symmetry. So when x is equal to 20, we're told that the height reaches its maximum, which is 12. So we can feed that information in, and that will allow us to find what the a is. So 12 is equal to a times 20, and then 40 minus 20, so it's going to be times another 20. So 12 is equal to 400a. A is equal to 12 over 400, which is 3 over 100, which is 0.03. So the connecting equation is that h is equal to 0.03x into 40 minus x. In part B, the ball passes over a horizontal bar perpendicular to the path of the ball. The bar is 3 meters above the ground, so that's about here. So we've got our posts 3 meters above the ground. Use the equation to find the greatest horizontal distance of the bar from O, from the origin. So the greatest horizontal distance is going to be here. So what we need to do is set our quadratic equation equal to 3. So 3 is equal to 0.03x 40 minus x. Now if we multiply this in, we're going to get 3 is equal to 1.2x minus 0.03x squared, which we multiply by 100, we'll get 300 is equal to 120x minus 3x squared, all to one side. 3x squared minus 120x minus 300 is equal to 0. And then if we divide by 3, x squared minus 40x minus 100 is equal to 0. Then you can use the quadratic formula or use your calculator with that equation solver. You'll get that x is equal to 20 plus or minus 10 root 3. Now if you do 20 plus, that one's going to give you the one furthest away, which is going to be here, and that on your calculator is 37.3. And if you do the 20 minus 10 root 3, you'll get this one here, which is 2.68, but the answer, the furthest away from O, is going to be the 37.3 meters. In part C, give one limitation of the model. Well, you can say maybe the ball is not kicked from the ground. Maybe somebody held it in the air and kicked it from a slight height, or maybe the ball was spinning in the air, or you've got air resistance, or the ground wasn't flat. You just have to list one limitation, so you can think of plenty there. This next question is an exponential model, modeling the value of a rare painting. So we've got here with V and T, and it would be this sort of shape with a V is equal to PQT equation. But we've linearized it and got a straight line, and we've done that by taking logs to both sides. And then using your log laws, because these are times together, you can say that that's log of P plus log of Q to the T. And then using your log law, that T can come down. So we've got log of V is equal to log of P plus T log of Q. And this is of the form y is equal to mx plus C, because V is in the y position, T is in the x position, so the y-axis intercept there, this would be here, log of P, and the gradient is the log of Q. Now we're told that the equation of the line is this equation here, so we can see the m, the coefficient in front of T, is 0.05, so that's telling me that log of Q is equal to 0.05. Log is log to base 10, so to find Q, 10 to the 0.05 is equal to Q. If you do that on your calculator, Q comes out to be 1.122, being asked to give it to 4SF. And then if we do the same with the y-axis intercept, we're told that that is 4.8. So 4.8 is equal to log to base 10 of P. So that tells us 10 to the 4.8 is equal to P. On our calculators, P comes out to be 63095.73. Doing it to 4SF, 63100. Part B, with reference to the model, interpret the constant P. So we've got V is equal to our 63100 times 1.122 to the T. So when T is 0, when we first get the painting, then the value is going to be 6310. So the P is the initial value of the painting. Now our Q, if you think 1.122 to the T, as T increases, this is going to tell us that the percentage increase is going to be 12.2%. So timesing something by 1 point, and then this bit here is the percentage increase. But we're asked for the whole value here, so the constant Q, the 1.122, is proportional to the rate of increase in value of the painting. In part C, find the value of the painting as predicted by the model on the 1st of January in 2010. So we've got it in 1980, so we need to calculate how many years later. That will be when T is equal to 30. So we just feed that in. V is going to be 63100 times 1.122 to the 30, and that gives us a value of 30 years later, 1994412. So that is going to be 2 million. In this question, we are modelling the fastest speed you can go in each of the gears as you work your way up the gears in a car by an arithmetic sequence first and then a geometric sequence. And we're told that the first gear, the fastest speed you can go in that, is going to be 28. So that's telling us that A is 28. Now, if we've got an arithmetic sequence, that goes A, and then A plus D, the common difference, A plus 2D for the third term. You are always one behind in the D, how many terms are long. So if we get to the sixth term is going to be A plus 5D is equal to 115. So if we just substitute that in there, 28 plus 5D is going to be 115. So D comes out to be 17.4. Now, being asked what's the fastest speed of the car in the third gear, that will be A plus 2D, which will be 28 plus 2 times the 17.4, which is 62.8. That will be kilometers per hour. In part B, we're using the same information, but now modelling it with a geometric sequence. So geometric sequence again starts with A, but then you are timesing between the terms by the common ratio. So it's AR squared, and so on. And the second term's just got 1R, the third term's got 3, so you're always one behind with the R's. But the first term again is 28. The sixth term is going to be AR to the 5 is 115. So when you've got a geometric sequence, you always put a future term divided by the previous, because then the A's will cancel. So AR to the 5 over A is going to be, putting in the position, 115 over 28. The A's will cancel, and if we take the fifth root of 115 over 28, that's what R will be, and that comes out to be 1.33. And then in B, we're being asked to find what's the fastest speed in the fifth gear, which is going to be AR to the 4. So that's going to be R28 times 1.33 to the 4, which is 87.6. In this next question, we're modelling the height above ground of a Ferris wheel with this trig equation. But first of all, in part A, we've got to express this in the harmonic form. So 10 cos theta minus 3 sine theta is equivalent to R cos of theta plus alpha. Now you get on the formula sheet the addition formulae, and the cos of theta plus alpha is going to expand to R cos theta cos alpha, and when it's plus in the middle for cos, it's minus R sine theta sine alpha. And now we equate coefficients. So what is being times by the cos theta is 10, and on the right, what is being times by the cos theta is R cos alpha. So 10 is equal to R cos alpha. We don't need to worry about the minus, that's already come from the addition formulae. So similarly, 3 is just equal to R sine alpha. And now we square and add. So 10 squared and 3 squared is 109. Squaring on the right, the trig term is going to have R squared cos squared alpha plus R squared sine squared alpha. I'll take R squared out as a common factor. Cos squared alpha plus sine squared alpha is equal to 1. So that will tell me that R is equal to the square root of 109. Now to find alpha, if you do 3 over 10, that will be equivalent to R sine alpha over R cos alpha. The R's will cancel, sine over cos is tan, so if we do inverse tan of 3 over 10, or 0.3, that's equal to alpha. Alpha is equal to 16.7 degrees. So we've found for part A, it's equivalent to 100 root 109 cos of theta plus 16.7. Now we've spotted that for part B, we've got a 10 here and a 3, which is similar to what we've been working with in part A, but the angle is 80t and in part A it was theta, so we're going to have to replace that. And we've also spotted that the signs are different. And it's telling us for part B that the initial height of the passenger above ground is 1 meter. So this thing is starting off with the passengers 1 meter high when t is equal to 0, and we need to find this constant here, alpha. So I'm going to leave it in this form to start with and feed in that h is equal to 1 when t is equal to 0. So we're going to have the alpha, and then if t is equal to 0, cos of 0 will be 1, so it'll be alpha minus 10, but when t is equal to 0, sine 0 is 0, and times by 3 will still be 0. So taking that minus 10 across, we're going to get that 11 is equal to alpha. So for part 1, making an equation, we've got that h is equal to 11 minus 10 cos of 80t plus 3 sine of 80t. Now part 2, hence find the maximum. So in order to find the maximum, we need to convert it from these two ratios in cos and sine and use what we found in part A. So in part A, we said that the 10 cos theta minus 3 sine theta was equivalent to root 109 cos of theta plus 16.7. And we've noticed that for our model we need minus and plus. So we need minus here and plus. So that's going to change the signs on the left. So we need to just change the sign there. So now we've got what we want in our equation, which is here. So we can just replace that with h being equal to 11 minus root 109 cos of 80t, replacing the theta, plus 16.7. So the maximum height is going to occur when this angle that we're taking cos of is going to be minus 1, and then that will times by the minus root 109 and give us a maximum height of h equal to 11 plus root 109. And if you do that on your calculator, that comes out to be 21.4 meters. Now for part C and D of the same question, we're modelling the height above ground of the Ferris wheel with our equation, which is h is equal to 11 minus root 109 cos of 80t plus 16.7. In part C, we're being asked to find the time for the passenger to reach the maximum height for the second cycle. So if we think about our transformations of graphs, we're moving the cos graph 16.7 to the left, we're squashing it in, we are stretching it, and we are reflecting it with this minus in the x-axis and then shifting it up 11. So the maximums are going to happen because of this reflection in the x-axis. The cos graph goes like this. We've shifted it to the left, but then because we've reflected it, it's gone like this. So these bits here are happening when this angle is at the cos being at its minimum, and they refer to these places here. So where does the cos graph have a minimum? At 180 degrees, so that would be the equivalent of the first maximum, but we want the second one, so if we go round again and add 360 on, will actually be at 540, and that will be where this one is. So we need to make the angle here, the 80t plus the 16.7 equal to 540, and if we just rearrange, take the 16.7 over and divide by 80, t comes out to be 6.54, which is 6 minutes and 32 seconds. Now for part D, it is decided to increase the profits so that the speed of the wheel is to be increased. So we need it to go round more times in the same time period, which is going to be a further squash in. And what was it that squashed it in? It was the 80 in front of the t. So how would you adapt the equation? You would increase the 80. For example, you might have h is equal to 11 minus root 109 cos of 90t plus 16.7. In this next question, we're modelling with this graph the speed that a train travels at when it's leaving Tokyo Station. And in part A, we're being asked to find the value of t. So that is here when the speed is equal to 0. So there's two places where the speed equals 0, either at the beginning or the end of this graph. So if this is our equation for B, we've just got to equate that to 0 and solve for the little t. And that will give us the two places where it goes through that x-axis, which is actually t on our x-axis. So we've got the ln of t plus 1 there. That's got to equal to 0 to find it. Now these two terms are being multiplied together, so that's either going to happen when 1500 minus 600t is equal to 0, or the ln of t plus 1 is equal to 0. Now we should know that the ln of 1 is equal to 0. So if t is equal to 0 here, we just have the ln of 1, and that's going to correspond to the origin, that place there. So that's going to happen when t is equal to 0. So the other one that we're looking for must be when 1500 is equal to 600t. So 1500 divided by 600 is equal to our t. T is equal to 2.5, and we're working in hours. In part B, we're being asked to show that the maximum speed of the train occurs when t is equal to this. So to find a max, we need to differentiate. So dv by dt. We can see we've got a product, so we're going to be using the product rule. So that is first differential of second, which differentiates to 1 over t plus 1, plus second, the ln of t plus 1, differential of first, which is minus 600. Now at a max, that is equal to 0. So if we take the second term over to the other side, and this t plus 1 I'll put underneath, is equal to 600, the ln of t plus 1. Now we've got to try and get this here. So we've made one of the t's the subject. It's not going to be the t in here. It's going to be either this t or this t. I've got to reduce the numbers. So I take a factor of 300 out first. It's going to be 5 minus 2t over t plus 1 is equal to 300 times 2, the ln of t plus 1. So that 2 looks good. Cancel by the 300s. Now I can't quite see what's gone on now. So what I might do is start with this and see how I can make this. And then that's kind of working backwards. But then just to make sure that I end up with this, I'll then have to work forwards again. So I might take this minus 1 to the other side. So this is going to be t plus 1 is equal to 7 over 2 plus 2, the ln of t plus 1. Cross multiply, 2 plus 2, the ln of t plus 1 is equal to 7 over t plus 1. Now that's looking good. I've got the t plus 1. I just want 2 the ln of t plus 1 on its own, so I'll take this 2 to the other side. 2 the ln of t plus 1 is equal to 7 over t plus 1 minus 2. Now I'll give this minus 2 the same common denominator, so I'll do a t plus 1 and take that line all the way across. So that will give me on the top 7 minus 2t minus 2 over the t plus 1, which is 7 minus 2, 5 minus 2t over t plus 1. So that's my little workings to see how to manipulate what I've got and end up with where I'm going. So what I need to do is make this 5 a 7 minus 2 minus 2t over the t plus 1 is equal to 2 the ln of t plus 1. Then I need to factorize, so 7 minus 2 t plus 1 over the t plus 1 equals 2 the ln of t plus 1. Then I need to split this up. We've got 7 over t plus 1 minus 2 t plus 1 over t plus 1. So they'll cancel, is equal to 2 the ln of t plus 1. Take that 2 to the side. 7 over t plus 1 is equal to 2 plus 2 the ln of t plus 1. Now just cross multiply. So 7 over the 2 plus the 2 the ln of t plus 1 is equal to t plus 1. And then just bring that over. So I've run out of room, but I'll just put that there. So I've proved and got there. So sometimes you do have to work backwards. I couldn't quite see what was going on, but working backwards and then seeing how to work forwards. In part C, we're being asked to use T1 as 1.05 and use iteration. So you need to type in 1.05 on your calculator, press equal so it's at the bottom of the screen, and then type all this in. But when you get to here, just press answer. So it puts that answer that it's at the bottom of the screen in. And if you press it and find that T3 is going to be equal to 1.0447, it wants it to 3 decimal places, so 1.045. And then in part 2, repeated iteration, you keep pressing the equals button, t will settle down to 1.042. So that's how many hours it takes to reach the maximum speed. Thanks so much for watching. I hope you found this video helpful. Please give it a like, subscribe to the channel, keep your eye out for any more videos I'm going to post on the run up to the exams. Best of luck in the exams this summer, and I'll see you on the next one.